Hey Chem 30s, today is going to be a really short lesson. It's just the connection between intermolecular forces and boiling point. So let's just get right into this. The boiling point of a molecule is dependent on really one thing: strength of intermolecular forces. The stronger the intermolecular forces, the more heat, the more energy it's going to require to pull those molecules away from each other to get them right breaking from the liquid stage into the gas phase. Remember, we got to break that connection in between the molecules, that intermolecular forces. Well, here is going to be the simple rules we use in Chem 20. This is much more complicated, but we're going to stick to these basics. Rule number one: the greater the number of intermolecular forces, the higher the boiling point. So if you have 3 intermolecular forces compared to only 2, the molecule with 3 intermolecular forces have a higher boiling point. Rule number 2: if we have a tie, both substances have 2 intermolecular forces, then we're going to go to the substance that has the most number of electrons. Because if you have the most number of electrons, you have a stronger London dispersion force. Therefore, you will have a higher boiling point. Now, then there's rule number 3. If there's a tie in the number of electrons, like in an isomer, then we're going to look at stackability, or how much contact there is between the two compounds or molecules. So what I would like to do is, let's do an example. Again, I know you've copied this, so now that we're thinking about this, we're going to pause. I know you've watched recently the notes on intermolecular forces. I would like you to decide in each of these 4 cases, who is the molecule or atom with the higher boiling point. But more importantly than that, you have to write down why. Pause the video right now and take a second in order to complete this. Okay, I am choosing HF. If you look at hydrogen fluoride, it has hydrogen bonding, dipole-dipole, and London dispersion forces. Hydrogen iodide only has dipole-dipole and London dispersion forces. Therefore, because HF has hydrogen bonding, right? Because to have hydrogen bonding, you got to be hydrogen bonded to fluorine, oxygen, or nitrogen. It's bonded to fluorine. Therefore, HF has a higher boiling point. Let's look at the second example. Helium versus argon. Okay. Now, both of these are noble gases. They're both just atoms. Therefore, argon is going to win because argon's a larger atom, which means it's got more electrons, which means it's got greater London dispersion forces. Okay. Example number 3. Oxygen versus Ch3Cl. In this case, CH3Cl is going to win. And again, I would think that you probably drew this one. Both of these guys have London dispersion forces because everything has London dispersion forces. However, where oxygen is nonpolar, CH3Cl is polar. And because it's polar, that means it's got the dipole-dipole interactions. So it's got 2 London dispersion forces compared to oxygen's 1. CH3Cl is going to win. And in our last example, and I might have to move my picture for this one, the winner is CH4. And the reason CH4 wins is because they both have London dispersion forces yet again, because everybody does. But neither of these two are polar. They both cancel out perfectly. But if we go back and we count up the electrons, carbon dioxide adds to more electrons than methane. Therefore, carbon dioxide has the higher boiling point in this example. Okay, there's one more I would like you to do. Can you please, on example number 2, rank these following compounds from highest to lowest boiling point? Give the one with the highest boiling point the number 1, then all the way down to the compound with the lowest boiling point with the number 4. Again, I want to see a justification of your answer. Pause your video and go through all the work you would do to figure out this question, please. Now, I went through the effort of drawing these, so I'm going to slide my part over here. I'm going to grab my pen out. And I think I have to move some things to get my pen to work here. So my pen has to work. There we go. Should work now. So let's move my picture again. Okay, so let's start on the far left and work our way over. In this example, we know it has London dispersion forces because everything is London dispersion forces. If we take a look here, nitrogen pulls harder than hydrogen. So we're going to have a dipole there. We're going to have a dipole there. We're going to have a dipole there. Therefore, when I add this up, we have a net dipole going up. So it does have dipole-dipole forces. Does it have hydrogen bonding? Remember, to have hydrogen bonding, it's got to be hydrogen bonded to fluorine, oxygen, or nitrogen. We have it bonded to nitrogen here. So we're going to give it hydrogen bonding. And last but not least, let's add up the number of electrons in case we have a tie. So nitrogen plus the 3 hydrogens, that means we have 10 electrons. Okay, let's do the second example. We have nitrogen, diatomic nitrogen, N2. It has London dispersion forces because everything has London dispersion forces. Again, if I look up the 2 electronegativities, they're the same, so it doesn't have dipole. If it doesn't have dipole-dipole, it doesn't have hydrogen bonding. And then again, we're going to add up nitrogen plus another nitrogen, and we're going to have 14 electrons, just in case we have a tie. And we didn't do that over here, so let's do that. Okay, hydrogen, we're going to do diatomic hydrogen. So again, it's got London dispersion forces because everything has LDF. Again, we look up hydrogens. They're both the same, so nobody's going to pull, so it doesn't have dipole-dipole. Since it doesn't have dipole-dipole, it will not have hydrogen bonding. And then we're going to add up the electrons, and this is going to be 2 electrons. And then last but not least, we have, looks like ethanol, and this has London dispersion forces. Now, this one's got a lot of little dipoles, so we're going to draw them in, and it's going to take a minute. So carbon pulls harder. And again, if you're not comfortable doing this as a stereochemical picture, if I don't make you, then please feel free to draw this as a structural picture, and then you can see things cancel out a little bit better. So these guys are going to cancel a little bit. It looks to me like we're going to get a dipole more or less coming up in this direction, roughly. So it certainly doesn't cancel out. I think everybody can tell that. So this does have dipole-dipole. If we take a look, here is hydrogen bonding. Hydrogen bonded to fluorine, oxygen, or nitrogen. So we have hydrogen bonding. And the number of electrons for this one is 26 electrons. So now we've got to go and we've got to rank these 1 through 4. The highest boiling point will be the one that has the most intermolecular forces. Notice, ethanol and ammonia has a tie. When we have the tie, the first thing we look at is number of electrons. Well, ethanol has 26, so this is going to get the number 1 for the highest boiling point. This one over here is going to get the number 2. Now we've got to figure out who is the next strongest or by far the most weak. Again, we have a tie again. 14 electrons compared to 2, so this one's going to be the 3rd strongest. And hydrogen, no surprise, is going to be absolutely dead last. Well, I hope you've found this quite easy to figure out. Again, you might need some of your older lessons in order to get this solved for yourself. Please go back and rewatch any video that you need to.